It's often remarked that reality can be far more peculiar than anything we could invent, and this sentiment finds its perfect expression in the study of black holes. These cosmic objects exceed the most creative fantasies of fiction writers, yet they are a scientifically confirmed aspect of our universe. The idea of black holes was first proposed back in 1783 by the Cambridge scholar John Michell. His logic unfolded like this. If you fire an object, like a cannonball, directly into the sky, gravity will impede its upward journey until it eventually stops and plummets back to Earth. However, should its initial launch speed surpass a specific value called the escape velocity, gravity's pull would be insufficient to halt it, allowing the object to travel onward indefinitely. For our planet, this speed is more than 11 kilometers per second, while for the Sun, it's a much greater 617 kilometers per second. While these speeds are far beyond what a real cannonball could achieve, they are insignificant next to the speed of light, which travels at 300,000 kilometers per second, enabling light to depart from both Earth and the Sun with ease. Michel, however, theorized the potential existence of stars so immense that their escape velocity would be greater than the speed of light. Such stars would be invisible to us, as any light they emitted would be inescapably drawn back by their gravity. He termed these objects dark stars, but today you know them by their modern name, black holes. To grasp the nature of black holes, you must first start with gravity, which is detailed in Einstein's general theory of relativity, a framework that also redefines our understanding of space and time. The dynamics of space and time are dictated by a collection of formulas that Einstein developed in 1915, which are now referred to as Einstein's field equations. Despite being the most delicate of nature's known forces, gravity possesses two significant advantages. First, its influence extends across enormous distances. For instance, Earth is kept in orbit around the Sun from 150 million kilometers away, and the Sun itself circles the galactic center at a distance of about 25,000 light-years. Second, gravity is exclusively an attractive force, unlike electrical forces which can repel as well as attract. These two characteristics ensure that for any star with sufficient mass, the gravitational pull among its particles will overwhelm all other forces, inevitably causing a gravitational collapse. Nevertheless, for a long time, the scientific community found it difficult to accept that a massive star could implode under its own weight, and couldn't foresee what would become of such an object. Even Albert Einstein, in a 1939 paper, contended that a star couldn't collapse because matter has inherent limits to its compressibility. Many scientists intuitively agreed with Einstein, but there was a prominent exception, the American scientist John Wheeler, who became a pivotal figure in the history of black holes. Throughout his research in the 1950s and 1960s, Wheeler insisted that numerous stars were destined for collapse and explored the profound challenges this presented to theoretical physics. He also foresaw many of the characteristics of black holes, the objects that stars transform into following their gravitational collapse. For the vast majority of its multi-billion-year existence, a star counteracts its own gravitational pull using the thermal pressure from nuclear fusion, the very process that converts hydrogen into helium. Eventually, though, the star depletes its nuclear fuel and starts to contract. It might, in some scenarios, stabilize as a white dwarf, which is a highly dense remnant of the star's core. However, in 1930, Subrahmanyan Chandrasekhar proved that a white dwarf cannot have a mass greater than 1.5 times that of our Sun. A comparable mass restriction for neutron stars was later determined by the Soviet physicist Lev Landau. This raised a critical question. What is the ultimate destiny of the countless stars that exceed these mass limits after they have consumed all their nuclear fuel? Robert Oppenheimer, widely known as the father of the atomic bomb, delved into this problem. In two papers published in 1939 with his students George Volkoff and Hartland Snyder, Oppenheimer demonstrated that such stars lack the necessary pressure to fend off collapse. Lacking this counteracting pressure, a uniform spherical star would compress down to a single point of infinite density, which is known as a singularity. All our established theories about the universe are built on the premise that space-time is fundamentally smooth and nearly flat. But at a singularity, where the curvature of space-time becomes infinite, these theories completely fall apart, signaling an end to space and time as we know them. Einstein was staunchly opposed to this conclusion. Soon after, the outbreak of World War II diverted the attention of most scientists, Oppenheimer included, toward nuclear physics, and the study of gravitational collapse was largely set aside. Interest was only reignited with the discovery of quasars, which are incredibly remote and luminous celestial objects. The first one, identified as 3C273, was found in 1963, and many more were soon observed. These quasars were astonishingly bright, considering their vast distances from us. The immense energy they radiated could not be accounted for by nuclear processes, which convert only a tiny portion of an object's mass into energy. The sole remaining explanation was the release of gravitational energy during a complete gravitational collapse, which brought the forgotten theory back into the spotlight. During such a collapse, gravity inexorably pulls in all nearby material, and it seemed obvious that a perfectly spherical star would shrink to a point of infinite density, a singularity. But what would happen if the star wasn't perfectly uniform or spherical? Could an asymmetrical collapse allow the stellar matter to miss the central point, and thus avoid forming a singularity? In a landmark 1965 paper, Roger Penrose proved that a singularity was unavoidable, based only on the fundamental fact that gravity is always an attractive force. At the point of a singularity, Einstein's equations are no longer valid, which has a profound implication. The future becomes fundamentally unknowable. This means that from the moment a singularity forms, the ability to predict what will happen next is completely lost. The process of stellar collapse must involve something truly remarkable. Yet this loss of predictability poses no threat to us, as long as the resulting singularity isn't naked, meaning it remains shielded from our observation. Roger Penrose put forth the cosmic censorship hypothesis, which suggests that every singularity created from a collapsing star is safely enclosed within a black hole. This term, coined by John Wheeler in 1967 and now universally recognized, describes a region of space-time where gravity is so powerful that light itself cannot break free. Given that countless efforts to challenge the cosmic censorship hypothesis have been unsuccessful, its validity is widely accepted. From an external viewpoint, the inner workings of a black hole are completely unknowable, as its appearance remains unchanged regardless of what material falls into it or its method of formation. This principle led to John Wheeler's famous declaration that black holes have no hair. Every black hole is defined by a boundary known as the event horizon, a point where the gravitational pull becomes so immense that it ensnares even light. Because the speed of light is the universe's ultimate speed limit, Anything that crosses this threshold is irrevocably trapped. The experience is much like canoeing toward Niagara Falls. Well away from the edge, you can still escape. But once you get too close, no amount of effort can prevent you from going over. In this analogy, the water's current quickens, yanking the front of the canoe more forcefully than the back, a process mirrored by a black hole's gravity. If you were to plunge in feet first, the gravitational force on your feet would be significantly stronger than on your head, stretching you vertically while squashing you horizontally. For a black hole only a few times more massive than our sun, this tidal force would rip you apart, turning you into spaghetti before you ever reached the event horizon. However, if you chose a supermassive black hole, millions of times the sun's mass, the gravity across your body would be nearly uniform, permitting a safe passage across the boundary. So, should you ever contemplate such a journey, I'd advise picking a truly enormous black hole, like the one residing in our galactic center, with a mass of 4 million suns. During your descent into the black hole, you personally wouldn't experience anything out of the ordinary at the moment you cross the event horizon. For someone watching from a safe distance, however, your journey would look very different. They would see your fall appear to decelerate dramatically as you approached the boundary. Your image would progressively shift toward the red end of the spectrum and grow dimmer, until you faded from sight completely, forever lost to the observable universe. Assuming general relativity holds true, and that the density of matter and energy is positive, which it almost always is, the surface area of a black hole's event horizon can never decrease. This means that whenever new material or radiation is captured, the boundary must expand. Furthermore, when two black holes collide to form a single larger one, the new event horizon's area must exceed the combined areas of the two originals. This principle, known as the area theorem, received experimental validation on September 14, 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, captured the gravitational waves from just such a merger. By examining the gravitational wave data from that event, scientists were able to deduce the mass and spin of the merging black holes, and with the no-hair theorem, they could then compute the areas of their event horizons. This revealed a remarkable parallel between the behavior of a black hole's surface area and a fundamental concept in classical physics: entropy. In the field of thermodynamics, entropy serves as a measure of a system's disorder, or how much information is missing about its precise internal state. The celebrated second law of thermodynamics dictates that entropy always trends upward, providing the first major clue to a profound link between these two fields. This parallel between the properties of black holes and the principles of thermodynamics can be taken even further. The first law of thermodynamics posits that a minor adjustment in a system's entropy corresponds to a proportionate change in its energy. In the context of black holes, a shift in mass is directly related to a change in the event horizon's area, with a value called surface gravity acting as the constant of proportionality. Following this analogy, if the event horizon's area is like entropy, then surface gravity, which measures the strength of the gravitational field at the boundary, is the equivalent of temperature. This comparison is strengthened because surface gravity is constant across the entire event horizon, much like the uniform temperature of an object in thermal equilibrium. While the correspondence between entropy and the area of the event horizon is compelling, The question of what this area truly represents remains. What precisely constitutes the entropy of a black hole? A pivotal breakthrough arrived in 1972 from Jacob Bekenstein, who was a graduate student at Princeton at the time. He suggested that after its formation via gravitational collapse, a black hole rapidly stabilizes into a state described by only three properties: its mass, its angular momentum, and its electric charge. This implies that the black hole's final form is completely detached from the nature of the material it consumed, whether it was made of matter or antimatter, or if the initial star was perfectly round or irregularly shaped. Put differently, identical black holes, sharing the same mass, spin, and charge, can be created from a vast number of different arrangements of initial matter. If you disregard the principles of quantum mechanics, this number of possible configurations would, theoretically, be infinite, as a black hole could be formed from a diffuse cloud containing countless particles of negligible mass. This raises a critical question. Is that number of potential starting states genuinely without limit? The answer lies in quantum mechanics, specifically with the uncertainty principle, which dictates that one cannot simultaneously know an object's exact position and its exact velocity. If you manage to measure an object's location with absolute certainty, its velocity becomes completely uncertain. And the reverse is also true. The practical consequence of this is that perfectly localizing any object is a physical impossibility. For instance, if you attempted to measure the size of something in motion, you would need to define its edges by knowing both their position and velocity at the same time, a task the uncertainty principle forbids. Therefore, you can never ascertain an object's precise dimensions. The uncertainty principle dictates that you can never precisely determine the true size of anything. This fundamental concept of quantum mechanics actually imposes a minimum size limit on all objects. For any given mass, there's a smallest possible size it can have, with this limit being smaller for more massive objects and larger for less massive ones, a direct consequence of wave-particle duality. Building on this, Jacob Bekenstein proposed that a black hole's entropy could be understood as a measure of the information that is permanently lost when a star collapses to form it. This idea, however, presented a critical paradox. If a black hole possesses finite entropy related to the area of its event horizon, it must, logically, have a temperature above absolute zero. This would require it to exist in thermal balance with its surroundings, a state that classical physics deemed impossible, as black holes were defined as perfect absorbers that emit neither light nor heat. This leads us to the central enigma of black holes. These incredibly dense objects formed from the remnants of collapsed stars. A key question is whether identical black holes can be formed from an infinite assortment of different stars, or if that number is finite. This very problem is known as the information paradox, and it remains one of the most profound challenges in all of theoretical physics. Every particle and force in the cosmos is thought to carry information. According to John Wheeler's famous insight, black holes have no hair, meaning that, as an observer, you can only determine their mass, charge, and spin from the outside. This implies an immense quantity of information is concealed within, hidden from your view. However, there's a physical limit to the information density of any region of space, because information requires energy, and energy has mass. As described by Einstein's equation E equals mc squared. If you pack too much information into one area, it will inevitably collapse into a black hole, whose size reflects the amount of information it contains, much like a library collapsing under the weight of too many books. If the volume of hidden information in a black hole is proportional to its size, then general principles suggest it must have a temperature and should radiate heat like a glowing piece of metal. Of course, this seemed impossible because everyone believed nothing could escape a black hole's gravity. This puzzle went unsolved until 1974, when I was investigating the behavior of matter near a black hole through the lens of quantum mechanics. To my astonishment, I found that black holes appear to emit particles continuously, behaving exactly like any other hot body. Initially, I was certain that black holes could not emit anything, and I tried everything I could to eliminate what I thought was a preposterous result. But the more I examined the problem, the more persistent the conclusion became, until I had no choice but to accept it. What finally convinced me of the reality of this physical process was that the emitted particles had a perfect thermal spectrum. My calculations showed that a black hole creates and radiates particles as if it were a hot object with a temperature directly proportional to its mass surface gravity and inversely proportional to its mass. This discovery made Jacob Beekenstein's controversial suggestion about a black hole's finite entropy suddenly compelling, as it explained how a black hole could be in thermal equilibrium at a non-zero temperature. Since that time, the mathematical framework for this thermal radiation from black holes has been independently verified by many other scientists, using a wide range of approaches. One way for you to visualize this radiation is to consider that quantum mechanics fills all of space with pairs of virtual particles and antiparticles. These pairs constantly materialize, separate briefly, and then annihilate one another. They are called virtual because they can't be observed directly with a particle detector. Even so, we can measure their indirect effects, which are confirmed by tiny fluctuations in the light spectrum of excited hydrogen atoms, a phenomenon known as the Lamb shift. When this process occurs at the edge of a black hole's event horizon, it's possible for one member of a virtual particle pair to be captured and fall in, leaving its partner without a counterpart for annihilation. This lone particle might then also fall into the black hole, or it could escape into deep space. To an external observer like you, this escaping particle would appear as radiation being emitted directly from the black hole itself. So, what would you experience if you were to fall into a black hole? The consequences are grim. If it were a stellar mass black hole, the immense gravitational gradient would stretch you into a thin stream of atoms before you even reach the horizon. Conversely, if you fell into a supermassive black hole, you could cross the horizon unscathed, only to be crushed out of existence at the central singularity. A black hole possessing the mass of our Sun would radiate particles so slowly that its emissions would be undetectable. However, it is theorized that much smaller, miniature black holes, perhaps with the mass of a mountain, could have formed in the chaotic and irregular conditions of the early universe. Such a mountain mass black hole would emit X-rays and gamma rays at a staggering rate of about 10 million megawatts, which is enough to supply all of Earth's energy needs. Yet harnessing this power would be an extraordinary feat. You couldn't place it in a power station, as it would simply fall through the floor and sink to the planet's core. The only plausible scenario for its use would be to place it into a stable orbit around the Earth. So far, all attempts to locate these miniature black holes have proven fruitless. There is, however, another fascinating possibility: that we could create them within extra dimensions of space-time. Certain theories propose that our universe is merely a four-dimensional membrane existing within a larger 10- or 11-dimensional reality. You can get a sense of what this might entail from the 2014 film Interstellar. We are unable to perceive these additional dimensions because light is confined to the 4 dimensions of our own universe and cannot travel through them. Gravity, on the other hand, is not so constrained and can exert its influence across these extra dimensions, where its force could be immensely stronger than what we experience. This suggests that forming a black hole in these dimensions would be significantly easier, and it is an event we might be able to witness at the Large Hadron Collider, or LHC, located at CERN. The LHC consists of a tunnel forming a ring with a circumference of 27 kilometers, where 2 particle beams are accelerated in opposite directions until they collide. Such collisions could, theoretically, generate miniature black holes, which would then decay by emitting particles with a very distinct and recognizable signature. As a black hole radiates these particles, its mass diminishes, causing it to shrink and accelerate the rate of emission until it eventually evaporates completely, disappearing from existence. This raises a profound question. What becomes of all the particles and any unfortunate astronauts that might have fallen into it? It appears that aside from its total mass and spin, all information about what constituted the black hole is lost forever. If this loss of information is real, it presents a fundamental challenge that strikes at the very core of our scientific understanding. For more than 200 years, we have operated under the principle of scientific determinism, which posits that the laws of science govern the universe's evolution. If black holes truly destroy information, we lose the ability to predict the future, as a black hole could emit any random assortment of particles. While incredibly improbable, it could theoretically produce a functioning television or a leather-bound collection of Shakespeare's works. Far more likely, it would emit thermal radiation, much like the glow from a piece of red-hot metal. You might think that our inability to predict the emissions of a distant black hole is of little importance, but this is a matter of fundamental principle. If determinism breaks down in black holes, it could potentially fail in other scenarios as well. There could be virtual black holes that emerge from the vacuum of space, consume one group of particles, release another, and then vanish. Even more unsettling, if determinism is not absolute, we can no longer be certain of our own past. Our historical records and even our memories could simply be illusions. The past defines who we are, and without it, we risk losing our very identity. It is therefore essential to discover whether information is genuinely lost in black holes, or if it can, in principle, be retrieved. For 40 years, this apparent loss, known as the information paradox, has perplexed scientists. And while many believe information must be conserved, no one had proposed a convincing mechanism for how it could be preserved. This remains one of the greatest unsolved mysteries in theoretical physics. Recently, new breakthroughs in the effort to unify gravity and quantum mechanics have revitalized the quest to solve the information paradox, with the concept of space-time symmetries being central to this progress. To understand this, imagine a scenario where gravity does not exist and space-time is perfectly flat, like a vast, featureless desert. This environment possesses 2 kinds of symmetry. The first is translational symmetry, meaning if you were to move from one point to another, you would observe no change. The second is rotational symmetry, meaning if you were to stand still and turn around, your view would be identical in every direction. These same symmetries are present in flat spacetime, the kind that exists without any matter. However, the moment you introduce something into this desert, such as a mountain, an oasis, or a few cacti, the symmetry is broken. The landscape now appears different depending on your location and the direction you are facing. This is precisely what happens in space-time. Placing objects within it breaks both translational and rotational symmetries, and this very act is what generates gravity. A black hole represents a region where gravity is incredibly intense, causing space-time to become severely warped. You would expect all symmetry to be broken within it, yet, as one moves farther away from the black hole, the curvature of space-time lessens until, at a great distance, it appears almost perfectly flat. It was here that Bondi, Metzner, Vanderburg, and Sachs made an astonishing discovery back in the 1960s. Far from any matter, space-time exhibits an infinite set of symmetries known as supertranslations. Each of these symmetries corresponds to a conserved quantity called a supertranslation charge. A conserved quantity is something that remains constant as a system evolves over time. This concept expands on more familiar conserved quantities. For example, energy is conserved if space-time is unchanging over time, and momentum is conserved if space-time appears the same from different points. The extraordinary part of the discovery of supertranslations is that they imply an infinite number of conserved quantities exist far from a black hole, offering an entirely new perspective on gravitational physics. We have long known that a black hole is characterized by three primary parameters: its mass, its charge, and its spin, which are all classical properties. However, it now seems a black hole also carries supertranslation charges. This suggests that black holes are far more complex than we once thought. They are not bald or described by just 3 hairs, but instead possess a vast amount of supertranslation hair, which could be the very mechanism that encodes all the information about what has fallen inside. It remains a possibility that supertranslation charges do not hold all the necessary data, and the missing pieces might be found in additional conserved quantities known as superrotation charges. These charges are tied to related symmetries called superrotations, a subject still shrouded in mystery. If this proves correct, and every piece of information about a black hole can be described by its hairs, it would suggest that information isn't lost after all. This concept has gained traction thanks to recent scientific inquiries, which propose that superrotation charges could fully explain the entropy of any black hole. Under this framework, quantum mechanics would be preserved, with all information being encoded on the event horizon, which is the surface of the black hole. The conventional properties we can measure, a black hole's mass, electric charge, and spin, would still exist outside this boundary. However, the event horizon itself would contain the supplementary data needed to fully account for everything that has fallen inside, complementing those 3 primary characteristics. The journey of discovery is ongoing, but a definitive solution to the information paradox has yet to be found. So, where did this all start? As Hamlet mused, I could be bounded in a nutshell and count myself a king of infinite space. Is our universe truly without end, or is it simply immense? If it had a genesis, is its existence eternal, or merely very long? How can our finite minds possibly grasp an infinite cosmos, and isn't it audacious to even make the attempt? I am convinced that we not only can but must endeavor to understand the universe, and our progress in comprehending it has already been extraordinary. While we don't have the full picture yet, I'm hopeful that it is within our reach. According to the lore of the Bushongo people in Central Africa, the beginning was a void of darkness and water, inhabited only by the great god Bumba. One day, a sharp pain struck Bumba's stomach, causing him to retch and vomit out the sun. The sun's heat then evaporated some of the water, revealing land. Still afflicted by pain, Bumba next brought forth the moon, the stars, and a variety of animals, including the leopard, crocodile, turtle, and, ultimately, humankind. This creation story, much like countless others, seeks to address the fundamental questions that preoccupy us. What is our purpose? And from where did we originate? The typical answer is that humanity is a relatively new phenomenon, a conclusion supported by the clear progression of our knowledge and technology. It seems logical that our species cannot have existed for a vast amount of time, or our advancements would be far greater. For instance, Bishop Ussher's calculations based on the Book of Genesis pinpoint the dawn of time to a specific moment, 6 o'clock in the evening on October 22nd, 4004 BC. In contrast, the physical world of mountains and rivers appears largely unchanged throughout human history, often viewed as a static backdrop that either existed eternally or was created alongside us. However, the concept of the universe having a beginning was not universally accepted. The renowned Greek philosopher Aristotle, for example, maintained that the universe has existed forever, believing that something eternal is inherently more perfect than something created. To account for human progress, he proposed that periodic floods or other cataclysms would regularly reset civilization to a primitive state. This belief in an eternal universe was often rooted in a desire to avoid invoking divine intervention for its creation and continued existence. The question of whether the universe had an origin was a source of deep contemplation for the German philosopher Immanuel Kant, who identified a logical contradiction, or antinomy, within it. If the universe did have a beginning, he questioned why an infinite expanse of time would have elapsed before it came into being. Kant referred to this as the thesis. Conversely, if the universe has always existed, he asked why it required an infinite duration to arrive at its current state. He called this the antithesis. Both sides of Kant's argument were built on his assumption, an idea he shared with most thinkers of his time, that time is absolute, flowing independently from an infinite past to an infinite future, with or without a universe. This perspective is still prevalent among many scientists today. Yet Einstein's theory of relativity in 1905 integrated space and time into a single concept, though it didn't elaborate much on the nature of space itself. It feels intuitive that space stretches out infinitely in every direction, as we don't imagine the universe terminating at a brick wall, even if no logical reason forbids it. With powerful instruments like the Hubble Space Telescope, we can now probe the deepest reaches of the cosmos, revealing billions upon billions of galaxies in a vast array of shapes and sizes. We observe giant elliptical galaxies alongside spiral ones, much like our own Milky Way, each containing countless billions of stars, many of which could host their own planetary systems. Although our own galaxy obstructs our view in certain directions, the overall distribution of galaxies throughout space appears remarkably uniform, aside from some local clusters and voids. The apparent decrease in the density of galaxies at extreme distances is merely an observational effect, as they are so remote that we lack the ability to resolve them. Therefore, we can confidently state that the universe seems to occupy all of infinite space, and is largely consistent no matter how far out we look. However, while the cosmos appears uniform at any given point in space, it is certainly not static. It demonstrably changes over time. This was a profound realization that didn't occur until the early 20th century. Before that time, The prevailing belief was that the universe was fundamentally unchanging and could have existed for an infinite duration. This idea, however, leads to illogical outcomes. If stars had been radiating energy for an eternity, they would have inevitably heated the entire universe to their own temperature. In such a scenario, the night sky would blaze as brightly as the sun, because any line of sight would ultimately terminate on the surface of a star or on a dust cloud heated to that star's temperature. The darkness of the night sky, therefore, holds a profound significance. It suggests that the cosmos could not have persisted eternally in its current form. Something must have occurred in the distant past to ignite the stars, and the light from the most remote ones simply has not had enough time to reach us, which explains why the heavens do not glow from every direction. If stars have existed forever, why did they suddenly ignite a few billion years ago? And what kind of cosmic clock told them it was time to shine? This very question troubled philosophers like Immanuel Kant, who was convinced the universe had always existed. Most people, however, were content with Bishop Ussher's calculation that the universe, much as you see it now, was created only a few thousand years ago. But during the 1920s, observations made with the 100-inch telescope at Mount Wilson Observatory started to show flaws in this theory. Edwin Hubble found that countless faint patches of light, which were called nebulae, were in fact other galaxies, enormous clusters of stars much like our sun, but located at incredible distances from us. For them to look so small and dim, they must be so far away that their light has taken millions or even billions of years to arrive here. A fact suggesting the universe couldn't have begun just a few thousand years ago. Hubble, however, discovered something even more remarkable. By analyzing the light from faraway galaxies, he was able to determine if they were moving toward or away from us. To his immense surprise, he realized that almost all of them were receding. Furthermore, the more distant a galaxy was, the faster it was moving away. The universe, in essence, is expanding, with all galaxies moving apart from each other. The discovery of the expanding universe was one of the greatest intellectual revolutions of the 20th century. It arrived as a complete surprise and drastically changed the debate surrounding the universe's origins. If galaxies are flying apart now, they must have been closer together in the past. Based on the current rate of expansion, we can calculate that 10 to 15 billion years ago, they were all extremely close to one another. It appears that at the beginning of the universe, everything was concentrated at a single point in space. Many scientists felt uneasy with the notion that the universe had a beginning, as it pointed to a breakdown of the laws of physics. Some chose to assign this phenomenon to an external factor, conveniently referred to as God. As a result, theories were proposed in which the universe is currently expanding but possesses no beginning. One such model was the steady-state theory, proposed in 1948 by Hermann Bondi, Thomas Gold, and Fred Hoyle. In this theory, the separation of galaxies is explained by the constant creation of matter in space, from which new galaxies form. This allows the universe to have always existed and to always look the same, a property that had the benefit of being a concrete prediction that could be tested by observation. A group of radio astronomers from Cambridge, led by Martin Ryle, conducted a survey of weak radio sources in the early 1960s. They found these sources were spread out with surprising uniformity across the sky and were located outside our galaxy. The weaker sources were farther away, and the stronger ones were closer. While the steady-state theory predicted a specific relationship between the number of sources and their strength, observations revealed more weak sources than expected. This finding indicated that the density of these sources was higher in the past, which contradicted the fundamental assumption of the steady-state theory, that everything remains unchanged through time. For this reason, among others, the steady-state theory was ultimately discarded. Another attempt to evade the idea of a universal beginning was the suggestion of an earlier, contracting phase of the universe. In this scenario, rotation and local irregularities in matter would have prevented everything from collapsing to a single point. Instead, clumps of matter would have missed each other, causing the universe to bounce and begin expanding again, ensuring its density would always remain finite. Two Soviet scientists, Yevgeny Lifshitz and Isaac Kalatnikov, asserted they had proven that a contraction lacking perfect symmetry would always result in a bounce with finite density. This claim was highly convenient for Marxist-Leninist dialectical materialism, as it avoided difficult questions about the creation of the universe, and thus it became an article of faith for Soviet scientists. You are used to the idea that events are caused by earlier events, which in turn were caused by events even earlier. This chain of causality stretches into the past. But imagine the chain has a beginning, a first event. What caused it? Few scientists have shown a willingness to confront this question. They have tried to avoid it, either by claiming the universe has no beginning, like the Russian scientists and steady-state theorists, or by insisting that the origin of the universe lies outside the scope of science, in the realm of metaphysics or religion. In my opinion, such a stance is unworthy of a true scientist. If the laws of science break down at the beginning of the universe, couldn't they also break down at other times? A law is not a law if it holds only some of the time. I believe we should try to understand the beginning of the universe on a scientific basis. It may be beyond our current capabilities, but the effort is worthwhile. If Einstein's general theory of relativity is correct, and certain reasonable conditions are met, the universe must have had a beginning. The mathematical arguments are difficult to refute, which is why Lifshitz and Kalatnikov eventually conceded that the universe must have had a beginning, even if the idea did not quite align with communist ideology. The progress of physics as a science was never held back by ideology. After all, physicists were needed to construct the atomic bomb, and its successful operation was non-negotiable. In contrast, Soviet ideology significantly hampered biology by outright rejecting the science of genetics. Observational data suggests that our universe originated from a Big Bang, an event where all existence was condensed into an infinitely dense point known as a space-time singularity. In this extreme state, Einstein's general theory of relativity breaks down, leaving us unable to even hypothesize about the universe's inception. It would appear, then, that the ultimate explanation for creation resides outside the reach of scientific inquiry. Concrete proof of the universe's incredibly dense origins appeared in October of 1965, with the detection of a faint cosmic microwave background permeating space. These are the same kind of microwaves your oven uses, only vastly weaker. They would cool a pizza to minus 271 degrees Celsius, which is far too cold to even defrost it. You have likely witnessed this radiation yourself if you recall analog televisions, as a small percentage of the static on an empty channel was a direct result of these microwaves from space. The most logical explanation for this cosmic background is that it's the residual radiation from a primordial, intensely hot and compact stage of the universe. As the cosmos expanded, this energy cooled down, becoming the faint echo we detect now. Frankly, the entire concept of a singularity marking the universe's beginning is something that neither I nor many of my colleagues are particularly comfortable with anymore. Near the Big Bang, Einstein's general theory of relativity fails, which is precisely why it's classified as a classical theory. It operates on an assumption that feels like common sense, that every particle possesses a distinct position and a specific velocity at any given moment. With this information, you could theoretically calculate the state of all particles at any point in the past or future. In the early 20th century, however, scientists realized they couldn't pin down what occurs at incredibly small scales. The issue wasn't a lack of better theories, but a fundamental randomness inherent in nature itself, an uncertainty that no theory can ever remove. This is encapsulated in the uncertainty principle, proposed by the German scientist Werner Heisenberg in 1927. He demonstrated that you cannot simultaneously measure a particle's position and its velocity with perfect accuracy. The more precisely you measure one, the less precisely you can know the other. Einstein famously detested the notion that the cosmos is governed by chance, capturing his sentiment in the well-known statement, "God does not play dice." Yet all evidence suggests that God is, in fact, an avid gambler. The universe functions much like a massive casino, constantly rolling dice and spinning roulette wheels. While the house might lose on any single bet, over a vast number of wagers the probabilities ensure an average outcome that favors them, which is precisely how casinos become so wealthy. The same principle applies to our universe. When the cosmos is vast, there are countless possible outcomes, allowing for predictable averages over large scales. However, in its infancy, when the universe was incredibly small, there were far fewer possibilities, and the uncertainty principle became the dominant force governing its state. To truly grasp the universe's origin, we have to merge the uncertainty principle with Einstein's general theory of relativity. This represents the most formidable challenge in theoretical physics today. Although we haven't completely solved this puzzle over the last 30 years, we are definitely making headway. When we try to predict the future, this uncertainty means we can't foresee a particle's exact path, but only calculate the likelihood of various outcomes, establishing a set of probabilities for the universe's evolution. Applying this logic to the past leads to a profound realization. The question, what existed before the Big Bang, becomes as nonsensical as asking, what is south of the South Pole? According to the concept of a self-contained universe, time itself is a property that exists only within our cosmos. So there is no before to refer to. Based on our current observations, we can calculate the probability for any given history of the universe, implying that countless possible pasts exist, each with a specific likelihood. There's even a potential history where England won the World Cup again, though its probability is admittedly quite small. This notion of multiple cosmic histories may sound like science fiction, but it is a genuine scientific concept. This idea comes from Richard Feynman, a brilliant physicist at the California Institute of Technology who famously played the bongos in his free time. He suggested that to comprehend reality, we must consider every possible history, assign each a probability, and use that sum to make predictions. This method is remarkably successful for forecasting the future, and it logically follows that it should apply to understanding the past as well. The current ambition of scientists is to weave together Einstein's general relativity and Feynman's concept of multiple histories into a unified theory that explains everything in the cosmos. Such a unified theory would grant us the ability to calculate the universe's evolution with incredible precision. However, even this ultimate theory wouldn't reveal how the universe originated or what its initial state was. To answer that fundamental question, something more is required. To understand the universe's origin, you first need to grasp what are known as boundary conditions, the rules governing what occurs at the very limits of space and time. If this edge were a normal point, you could simply cross it and consider the area beyond as an extension of our universe. However, a significant problem arises if this boundary is a singularity, a distorted edge where space-time is warped and density becomes infinite, making it nearly impossible to establish any sensible rules. The requirements for such conditions are entirely unknown, and there is no compelling logical argument for choosing one set of rules over any other. This leads to the intriguing possibility that the universe might simply lack any boundaries in space or time. While this idea seems to fly in the face of geometric theorems indicating that the universe must have a starting point, a temporal boundary, there is a fascinating resolution. While working to refine the mathematical methods of Richard Feynman, scientists introduced a concept they termed imaginary time. It is crucial to understand that this has no connection to the real time you and I perceive in our daily lives. The unique property of imaginary time is that it is boundless, and therefore sidesteps the entire issue of boundary conditions, a concept I refer to as the no-boundary proposal. Accepting that the universe has no boundary in imaginary time leads to a profound conclusion. It does not possess just one single history. Instead, this framework allows for a multitude of histories in imaginary time, each one corresponding to a distinct history in real time. Consequently, this implies an enormous number of potential universal timelines, which in turn influences the specific history that we happen to inhabit. When you survey this immense landscape of probable cosmic histories, it becomes clear that the vast majority would never lead to the formation of galaxies and stars, which are prerequisites for our evolution. Although the emergence of intelligent life without these celestial structures is not strictly impossible, it is exceptionally improbable. This means our very existence as conscious beings asking these questions acts as a powerful filter, constraining the possible histories we could be part of. It seems we find ourselves in one of the rare histories where galaxies and stars did indeed form, a line of reasoning known as the anthropic principle. In essence, it proposes that the universe must have the properties we observe for a simple reason. Had it been different, no observers like us would have been around to see it. Many scientists are skeptical of the anthropic principle, often viewing it as an artificial construct with little predictive capability. Nevertheless, the principle can be articulated with precision, making it a valuable tool when exploring cosmic origins. This is especially relevant to M-theory, currently our most promising candidate for a unified theory, which itself predicts a vast number of possible universal histories. The overwhelming majority of these potential histories are entirely hostile to the evolution of intelligent life. They might be devoid of matter, exist too briefly, or have a space-time that is excessively warped. Richard Feynman's concept of multiple pasts actually suggests that such inhospitable histories are highly probable, but from our perspective, the sheer number of lifeless histories is irrelevant. Our focus is solely on the small fraction where intelligent beings can emerge. It is important to note that this intelligent life would not need to be human-like. It could take the form of small green creatures who might be vastly more advanced, especially since humanity's track record of intelligent behavior is not always something to be proud of. To illustrate the power of the anthropic principle, let's examine the number of dimensions in our universe. Your everyday experience tells you that we exist in a three-dimensional space, where any location can be pinpointed using just 3 coordinates, like latitude, longitude, and altitude. But why is space specifically three-dimensional, rather than having 2, 4, or any other number of dimensions, as often depicted in science fiction? M-theory actually postulates that space consists of 10 dimensions, plus an additional one for time. The prevailing idea is that 7 of these spatial dimensions are compacted into a tiny, curled-up state, leaving the 3 we experience as large and relatively flat. You can visualize this with a drinking straw, which has a 2-dimensional surface, but because one dimension is rolled into a circle, it looks like a 1-dimensional line from afar. So, why don't we inhabit a universe where 8 dimensions are compact, leaving only 2 for us to perceive? A key reason lies in biology. A 2-dimensional creature would face insurmountable challenges with digestion. If it had an internal digestive tract similar to ours, this tract would effectively split its body in half, causing the organism to fall apart. Simply put, 2 flat dimensions do not provide the necessary complexity for intelligent life to arise. It turns out there is something fundamentally unique about a 3-dimensional existence. In 3 dimensions, gravity adheres to the inverse square law, a principle first identified by Robert Hooke in 1665 and later perfected by Isaac Newton. This law dictates that as the distance between 2 objects doubles, the gravitational pull between them weakens to 1/4 of its original strength. Tripling the distance reduces the force to 1/9, and so on, which is precisely what allows for the stable planetary orbits you see in our solar system. Now, imagine a universe with 4 spatial dimensions. In such a reality, gravity would follow an inverse cube law, meaning doubling the distance between objects would reduce the gravitational force by a factor of 8. This critical shift would make stable planetary orbits impossible. Planets would either spiral into their stars or be flung out into the desolate cold of deep space. At a smaller scale, electrons would be unable to maintain stable orbits around atomic nuclei, causing all matter as you know it to disintegrate. Consequently, if the concept of multiple histories permits numerous nearly flat spatial dimensions, it is only within histories featuring 3 such dimensions that intelligent life could arise. This unique condition is precisely why you can even pose the question of why space is 3-dimensional, as it appears to be a prerequisite for the observers who ask it. Among the most astounding characteristics of the cosmos you observe is the cosmic microwave background, a discovery made by Arno Penzias and Robert Wilson. This phenomenon is essentially the afterglow of electromagnetic energy from the universe's infancy. This background radiation is astonishingly uniform across the entire sky, showing variations of merely 1 part in 100,000, a level of smoothness so extreme that it demands a compelling explanation. The consensus explanation for this uniformity is a historical period of fantastically rapid expansion, where the universe grew by a factor of at least 1 billion trillion. This event is known as inflation, a process that, unlike the price inflation that often concerns us, was profoundly beneficial for the cosmos. However, if inflation were the only factor, the microwave background would be perfectly smooth, which raises the question of where its subtle variations originated. These tiny imperfections are the result of quantum fluctuations, an unavoidable outcome of the uncertainty principle. Remarkably, these minute fluctuations served as the primordial seeds for every structure that populates our universe, from galaxies and stars all the way to ourselves. The fundamental concept behind this is quite similar to the process that generates what is known as Hawking radiation at the event horizon of a black hole. This theoretical framework was fully developed a decade before the Cosmic Background Explorer, or COBE, satellite finally detected these predicted fluctuations in the microwave sky in 1993, demonstrating a case where theory significantly preceded observation. A decade after that, in 2003, cosmology evolved into a precision science with the initial results from the Wilkinson Microwave Anisotropy Probe, or WMAP. This mission delivered an extraordinary map of the cosmic microwave sky, giving us a snapshot of the universe when it was tens of thousands of times younger than it is today. The deviations WMAP observed were precisely what inflation had predicted, signaling that some areas of the early universe possessed slightly greater density than others. In these denser regions, the pull of gravity slowed cosmic expansion, eventually causing matter to collapse inward and form the first stars and galaxies. When you look at a map of the microwave sky, you are therefore viewing the very blueprint for the structure of the entire universe, a testament to the fact that we are all products of quantum fluctuations from when the universe was in its earliest moments. Today, the Planck Space Telescope has succeeded WMAP, charting the cosmos with much greater detail and putting our theories to even more rigorous tests. Scientists hope that Planck might even uncover faint traces of gravitational waves, another prediction of inflation, which would serve as a celestial signature of quantum gravity itself. This leads to the profound question of whether other universes might exist, a possibility suggested by M-theory, which posits that an immense number of universes could emerge from nothing across a wide array of different possible histories. Each of these hypothetical universes would have its own set of possible histories and future states, and it is likely that most of them would be utterly unlike the one we inhabit. The first tangible evidence supporting M-theory's hypotheses might come from the Large Hadron Collider, or LHC, a particle accelerator at the European Organization for Nuclear Research, known as CERN, near Geneva. While the LHC operates at what M-theory considers low energies, we might be fortunate enough to see the first hints of its validity, such as the discovery of supersymmetry. I'm convinced that finding the supersymmetric partners of the particles we already know would fundamentally alter our comprehension of the universe. In 2012, the LHC's discovery of the Higgs boson was announced, marking the first time a new elementary particle had been found in the 21st century. Hope remains that the LHC will also find evidence of supersymmetry. But even if it does not, the next generation of accelerators may succeed. The instant of the Big Bang represents the ultimate high-energy laboratory, providing the perfect conditions for testing M-theory and our ideas about how the basic components of space-time and matter were created. Astrophysical research into this era may offer vital clues in our quest to unify all the forces of nature. So while other universes might well be real, it is unfortunate that we will likely never have the means to explore them directly. We have gained significant insight into cosmic origins, yet two fundamental questions persist. Will the universe have an end? And is it truly unique? The most probable future for our universe depends entirely on the total amount of matter it contains. If this quantity is above a specific critical value, the mutual gravitational pull of galaxies will eventually halt expansion and draw everything back together into a final big crunch, bringing the history of our universe to a close. Conversely, if the universe's density is below that critical threshold, gravity will be too feeble to stop the galaxies from drifting apart forever. In that scenario, all the stars will eventually burn out, leaving the cosmos to become progressively colder and emptier. This would also be an end, just a far less dramatic one. Either way, we still have a few billion years before any of this becomes an immediate concern. Throughout this discussion, I have aimed to shed light on the origin, future, and fundamental properties of our universe. In its earliest moments, the cosmos was infinitesimally small and dense, yet that tiny point contained the entirety of what was to become our reality. In that sense, Hamlet was correct when he said that one could be bounded in a nutshell and count oneself a king of infinite space. And this all leaves us with one final, lingering question. Is there other intelligent life out there in the cosmos? I'd like to reflect on the emergence of life in the cosmos, focusing on intelligent life, a classification that has to include our own species, even though a great deal of human history reveals behavior that is profoundly irrational and detrimental to our own survival. I want to examine two central questions. What are the odds of life existing elsewhere in the universe, and what might the future hold for its evolution? It's a common-sense notion that things tend to become more disorderly and chaotic over time. This perception is actually backed by a scientific principle, the second law of thermodynamics, which states that the total amount of disorder, or entropy, in the universe is always on the rise. However, this law refers only to the total entropy. It is entirely possible for order to increase within a specific system, like an organism, as long as the disorder in its surroundings increases by an even greater amount. This is precisely the mechanism that underpins living things. We can characterize life as an ordered system that maintains itself against the natural drift towards disorder, and is also capable of reproducing, that is, creating similar, independent, ordered systems. To achieve this, the system must convert energy from an ordered state, such as sunlight or food, into a disordered state, namely heat. In doing so, the system fulfills the requirement of increasing total universal disorder, while simultaneously enhancing the order within itself and its descendants. For complex beings like you and me, life generally consists of two key parts: a collection of instructions dictating how the organism should function and reproduce, and a mechanism responsible for executing those instructions. In biology, we refer to these components as the genome and the metabolism. It is crucial to understand, however, that there is nothing intrinsically biological about this arrangement. A computer virus, for example, is a program that makes copies of itself in a computer's memory and spreads to other machines, which perfectly matches the definition of a living system I've just provided. Much like a biological virus, a computer virus represents a rather stripped-down form of life, possessing only instructions, or genes, without its own metabolic processes. It operates by co-opting the metabolism of its host, whether that's a biological cell or a computer. Some people question whether viruses truly qualify as life because they are parasites that rely on other living things to exist. By that logic, however, most forms of life, including us, would also be considered parasites, since we depend on consuming other life forms for our own survival. I am convinced that computer viruses should be seen as a form of life. It might reveal something significant about human nature that the only life form we have managed to create so far is one that is purely destructive in its function. I plan to touch upon electronic life forms again later. The life we are most familiar with is built upon chains of carbon atoms, with other atoms like nitrogen or phosphorus occasionally included. While one could theorize about life founded on a different element, such as silicon, carbon appears to be the most suitable candidate due to its unmatched versatility in forming diverse chemical bonds. The very existence of carbon atoms, with their specific properties, is contingent upon the meticulous fine-tuning of several physical constants, including the scale of quantum chromodynamics, the electric charge, and even the number of dimensions in spacetime. If any of these constants were significantly different, carbon nuclei would either be unstable or their electrons would collapse into the nucleus. This remarkable precision in our universe might initially seem wondrous, perhaps suggesting it was intentionally designed to support the emergence of humanity. However, it's essential to approach such conclusions with caution because of a concept known as the anthropic principle. This principle asserts that our theoretical models of the universe must be consistent with the fact of our own existence. It is rooted in a simple truth. If the cosmos were not conducive to life, we wouldn't be around to wonder why it seems so perfectly calibrated for us. The anthropic principle is typically discussed in two forms, the strong version and the weak version. The strong anthropic principle proposes the existence of numerous different universes, each governed by its own set of physical constants. Only within a very narrow range of these constants could building blocks for living systems, like carbon atoms, ever form. Since we must inhabit one of these universes, it shouldn't be a surprise that we find our physical constants to be so finely tuned. If they weren't, we simply wouldn't be here. I find this principle somewhat unsatisfying, as it's unclear what practical relevance all these other universes could have if they are forever separate from our own and unable to influence us. For this reason, I personally favor the weak anthropic principle. This approach takes the values of the physical constants as a given, and instead seeks to determine what can be inferred from the fact that life has appeared on this planet at this particular point in the universe's history. 13.8 billion years ago, at the moment of the Big Bang when the universe began, carbon did not exist. The universe was so intensely hot that all matter was confined to the form of particles we call protons and neutrons. In the very beginning, there were roughly equal numbers of protons and neutrons, but as the universe continued to expand, it also began to cool. Approximately 1 minute after the Big Bang, the temperature is thought to have dropped to about 1 billion degrees, 100 times hotter than the sun's core. At this temperature, neutrons started to decay, transforming into more protons. Had this been the only process occurring, all matter in the universe would have eventually been composed of the simplest element, hydrogen, whose nucleus consists of a single proton. During the universe's infancy, some neutrons managed to fuse with protons, which resulted in the creation of helium, a simple element with a nucleus containing 2 protons and 2 neutrons. However, the cosmos was not yet able to produce heavier elements like carbon and oxygen. It's nearly impossible to conceive of any living thing made up of only hydrogen and helium, and in any case, the universe was far too hot for atoms to even begin forming molecules. As the universe underwent continuous expansion and cooling, certain areas developed slightly greater densities than their surroundings. Within these denser pockets, the enhanced gravitational pull eventually halted the expansion and initiated a collapse. This gravitational collapse of matter led to the formation of the first stars and galaxies, a process that began approximately 2 billion years after the Big Bang. The earliest stars were likely much more massive than our Sun, possessing incredibly high internal temperatures. These extreme conditions acted as cosmic furnaces, transforming the primordial hydrogen and helium into heavier elements like carbon, oxygen, and iron. After hundreds of millions of years, some of these stellar giants exploded as supernovae, dispersing their newly forged heavy elements across space and providing the essential building blocks for subsequent generations of stars. Since most stars are too distant for us to directly observe their planetary systems, we rely on indirect methods to find them. The first technique involves carefully monitoring a star's light for any fluctuations. Should a planet's orbit cause it to pass between its star and an observer on Earth, it will create a small, temporary dip in the star's brightness. If this dimming occurs at regular intervals, it strongly indicates the presence of an orbiting planet. The second method requires the precise measurement of a star's position in space. An orbiting planet's gravitational pull will cause its parent star to wobble slightly. If this oscillation is observed to be regular and repeating, we can confidently infer that at least one planet is circling the star. These techniques were first implemented about 20 years ago and have since enabled the discovery of several thousand planets, with current estimates suggesting that 1 in 5 stars hosts an Earth-like planet within a life-friendly zone. Our own solar system came into being roughly 4.5 billion years ago, which is a little under 9 billion years after the Big Bang, coalescing from a cloud of gas enriched with the remnants of earlier stars. Earth itself is composed mostly of these heavy elements, including substantial amounts of carbon and oxygen. It was here that individual atoms somehow organized themselves into the complex molecules of DNA, the renowned double helix structure identified in the 1950s by Francis Crick and James Watson. The two intertwined strands of the DNA helix are connected by pairs of nucleotides. There are 4 types of these chemical bases: adenine, cytosine, guanine, and thymine. A fundamental rule dictates that adenine on one strand always pairs with thymine on the other, just as guanine always links with cytosine. This strict pairing means the sequence on one strand precisely defines the complementary sequence on its partner. This complementary structure allows the 2 strands of DNA to separate, with each serving as a perfect template for building a new, matching strand. This mechanism enables DNA to faithfully replicate the genetic information stored in its nucleotide sequence. Furthermore, specific segments of this code are used to manufacture proteins and other chemical compounds, which in turn execute the instructions encoded in the DNA and gather the raw materials needed for its reproduction. This complementary structure allows the 2 strands of DNA to separate, with each serving as a perfect template for building a new, matching strand. This mechanism enables DNA to faithfully replicate the genetic information stored in its nucleotide sequence. Furthermore, specific segments of this code are used to manufacture proteins and other chemical compounds, which in turn execute the instructions encoded in the DNA and gather the raw materials needed for its reproduction. As I noted, the original appearance of DNA remains a profound mystery, as the probability of such a complex molecule forming through random chance is astonishingly low. This has led some to propose that life was seeded on Earth from an extraterrestrial source, perhaps arriving on debris from Mars during the solar system's early years' chaotic youth, or as seeds of life drifting through the galaxy. The major challenge for this idea, however, is that DNA is unlikely to survive long-term exposure to intense cosmic radiation. If the origin of life on any given planet is an event of extremely low probability, it would logically require an immense amount of time to occur. Following that, an adequate period must also be available for the evolution of intelligent beings like us, all before our sun swells and consumes the Earth. This entire process is confined to the sun's lifespan of about 10 billion years, within which an intelligent species would need to develop interstellar travel to ensure its survival. Without a means of escape, all life on Earth is ultimately fated for extinction. The fossil record shows that the first forms of life emerged on Earth approximately 3.5 billion years ago. This happened only 500 million years after our planet had stabilized and cooled enough to become habitable. Given that the universe had already existed for about 7 billion years, there seems to have been more than enough time for beings like us to arise and begin questioning our own origins. So, if life is supposed to be incredibly rare, why did it appear on Earth only a quarter of the way into its available time window? The remarkably early arrival of life on our planet suggests that, under the right conditions, the spontaneous formation of life might actually be highly probable. It's possible that simpler organizational structures existed first, paving the way for the eventual development of DNA. Once DNA emerged, its efficiency was so great that it likely outcompeted and completely replaced any preceding biological systems, though we have no direct evidence of what these earlier forms might have been. One leading candidate for a precursor to DNA is RNA. RNA is chemically similar to DNA, but is a much simpler single-stranded molecule without the double helix form. Crucially, short strands of RNA can replicate themselves much like DNA can, making it plausible that life began in an RNA world and gradually evolved the more complex DNA structure. While we can now synthesize RNA and DNA in a laboratory, we have not yet managed to create their nucleotide building blocks from non-living matter. However, considering that for 500 million years, vast oceans covered nearly the entire planet, it is plausible that RNA could have arisen by chance amidst the planet-wide chemical reactions. The self-replication of DNA is not a flawless process, and random errors or mutations can occur. While most of these errors are harmful and can lead to extinction, and many are neutral, a small fraction prove beneficial. It is these advantageous errors that are preserved and promoted through Darwinian natural selection, driving the ongoing process of evolution. In its earliest stages, biological evolution unfolded at an incredibly gradual pace, requiring 2.5 billion years for the first primitive cells to develop into multicellular organisms. Over the subsequent billion years, this process continued, as some of these complex organisms evolved into fish, and a subset of those fish eventually transitioned into mammals. Since that time, the tempo of evolutionary change has quickened significantly, with the journey from the first mammals to us taking a mere 100 million years, which required only minor adjustments since early mammals already possessed their own versions of our essential organs. The development of humanity has reached a pivotal moment, one as significant as the emergence of DNA itself. The creation of language, particularly in its written form. This innovation opened up new pathways for transmitting information between generations, moving beyond the purely genetic inheritance carried by DNA. Although we can point to several distinct modifications in human DNA over the 10,000 years of recorded history, The amount of knowledge passed down through writing has expanded beyond measure, with the added benefit that this information can be revised and updated far more rapidly. Our own evolutionary path from early ape-like ancestors spanned several million years, during which the useful data stored in our DNA likely changed by only a few million bits. This prompts a fascinating question. If intelligent life exists beyond Earth, must it take on forms we would recognize? Or could it be entirely different? And perhaps more pointedly, can we confidently say that intelligent life exists even here on our own planet? Joking aside, if such beings do exist elsewhere, they are likely so distant that we have yet to encounter them, because I believe a visit would be unmistakable, and probably resemble something from a film like Independence Day. While genetic engineering could, in theory, prolong the existence of DNA-based life for at least another 100,000 years, it is far simpler to dispatch machines into the cosmos, a feat nearly within our grasp today. We have the capability to design these machines for the immense durations required for interstellar voyages. Upon reaching a new star, they could land on a habitable planet, extract the necessary minerals to replicate themselves, and then launch their progeny toward even more remote star systems, giving rise to a new form of life founded on mechanical and electronic parts, rather than complex organic molecules. Over vast timescales, this mechanical life could ultimately succeed DNA-based organisms, much as DNA itself may have supplanted earlier, more primitive forms of life. This raises the question of what the odds are that we will encounter an alien life form as we explore the galaxy. If our understanding of the timeline for life's emergence on Earth is accurate, there should be a great number of stars with life-bearing planets, some of which are billions of years older than our own. So, why do we not see the galaxy filled with self-replicating biological or mechanical entities? I must admit, I find the claims of UFOs carrying extraterrestrial visitors to be highly unconvincing. It is my firm belief that an actual alien visitation would be far more conspicuous, and in all likelihood, an extremely unsettling event. The profound question, then, is why no one has come to visit us. One possibility is that the spontaneous emergence of life is so extraordinarily rare that Earth is the only planet in the entire galaxy, or perhaps the observable universe, where it has ever occurred. A second explanation suggests that while self-replicating systems like cells might form with some regularity, the vast majority of these life forms never progress to intelligence. We often assume that intelligence is an inevitable outcome of evolution, but the anthropic principle cautions us against such thinking. It seems more plausible that evolution is a random walk through countless possibilities, with intelligence being just one of many potential results, and not necessarily one that guarantees long-term survival. After all, bacteria will likely persist long after human activities may have eliminated all other life. The sheer amount of time it took for life on Earth to advance from single cells to the multicellular organisms that precede intelligence, a staggering 2.5 billion years, supports this idea. This duration represents a substantial portion of the time available before our sun expands and dies, which aligns with the hypothesis that the probability of life evolving intelligence is vanishingly small. If this is true, we might discover many worlds with simple life, but it's unlikely we will ever find intelligent counterparts. There is also the chance that life is frequently prevented from evolving intelligence by catastrophic events, such as a collision with an asteroid or comet. In 1994, we witnessed comet Shoemaker-Levy strike Jupiter, creating a series of massive fireballs. It is widely thought that a smaller impact on Earth 66 million years ago caused the extinction of the dinosaurs. While some small mammals survived, any creature the size of a human was almost certainly annihilated. Such devastating impacts are estimated to occur roughly every 20 million years. If that frequency is accurate, it implies that intelligent life developed on Earth only because of a lucky streak, a 66 million year period free from such a cataclysm. Other planets in the galaxy that may have harbored life might not have enjoyed such a long, stable interval required for intelligent beings to evolve. A third, more somber possibility is that life does regularly evolve intelligence, but at that point, the system becomes unstable, and the intelligent species brings about its own destruction. This is a deeply pessimistic view, and one I sincerely hope is wrong. I lean toward a fourth option, that other intelligent life is out there, but we have so far failed to notice it. Through the Breakthrough Listen project, the sky is being monitored by 2 radio telescopes outfitted with cutting-edge technology. This initiative is well-funded, with thousands of hours of observation time, making it the largest scientific endeavor in history dedicated to discovering proof of extraterrestrial civilizations. Alongside this, the Breakthrough Message Project is a worldwide contest to craft a message comprehensible to an advanced species. However, until we achieve a higher level of development ourselves, we should proceed with caution regarding any potential answers. At this point in our history, interacting with a more sophisticated civilization could be tragically similar to the encounter between Native Americans and Europeans. Americans and Columbus, and I seriously doubt that meeting was a welcome one for the indigenous people. So, should we even be exploring space? What is the ultimate purpose? And how can we possibly justify the immense resources spent just to retrieve a few rocks from the moon, when there are pressing issues right here on Earth? The answer is all around you. To remain on our planet is to be like a castaway on a deserted island who makes no attempt to escape. We must investigate the solar system to locate other places suitable for human life. The situation bears a striking resemblance to Europe before 1492, when many likely argued that funding Columbus's venture was a fool's errand. Yet, the discovery of the New World profoundly reshaped the Old. Just try to envision a world without Big Macs or KFC. Our expansion into the cosmos will have an even more transformative impact. This cosmic expansion will fundamentally alter the course of humanity, and could very well decide if we have a future at all. While it won't resolve our immediate terrestrial problems, it will offer a new framework for understanding them, shifting our focus from the past to the future. It's my hope that this endeavor will unite our species to confront our shared challenges. This is, of course, a long-term strategy, and by that I mean a plan spanning hundreds or perhaps even thousands of years. We could establish a lunar base within 30 years, land on Mars within 50, and explore the moons of other planets within 200 years. I'm referring specifically to manned missions. Robotic explorers are already navigating the surface of Mars, and we have successfully landed a probe on Titan, one of Saturn's moons. But if we are genuinely concerned with the long-term survival of our species, we must make these journeys ourselves. Space travel is undeniably expensive, but it would only consume a tiny portion of the world's total resources. Since the Apollo missions, NASA's budget has been relatively stable in real terms, yet it has shrunk from 0.3% of the U.S. gross domestic product, or GDP, in 1970 to just 0.1% in 2017. Even a 20-fold increase in the global budget for space exploration would still represent a minuscule fraction of the world's GDP. Naturally, some will contend that these resources are better allocated to solving Earth's immediate crises, like climate change or pollution, rather than being invested in what could be a one-way trip to nowhere. But on July 20th, 1969, when Neil Armstrong and Buzz Aldrin set foot on the moon, the future of humanity was changed forever. The space race ignited a widespread passion for science and drove rapid technological advancement. Inspired by the lunar landings, many of today's leading scientists chose their careers to better understand ourselves and our position in the cosmos. Entirely new perspectives were unveiled, allowing us to see our planet as a single, interconnected whole. However, following the final moon landing in 1972 and the absence of further manned missions, public fascination with space began to fade. This decline coincided with a broader disillusionment with science in the Western world, as its many benefits failed to resolve the social issues that were capturing public attention. A renewed program of manned spaceflight could be instrumental in rekindling public excitement for space and for science more broadly. While robotic missions are far more economical and can yield more scientific data, they simply don't captivate the public imagination or advance humanity's physical presence in space, which, I must emphasize, should be our ultimate long-term goal. Proposals to create a lunar base by 2050 and to land humans on Mars could reinvigorate the space program, giving it a powerful new sense of purpose, much like President Kennedy's declaration did in the early 1960s. In late 2017, Elon Musk revealed SpaceX's ambitions to build a base on the Moon and launch a manned mission to Mars by 2022. Furthermore, President Trump signed a directive refocusing NASA on exploration and discovery, so it's possible we might reach these milestones even earlier. A renewed focus on space exploration could significantly elevate the standing of science within society. The diminishing prestige of scientific careers has grave implications. We inhabit a society deeply dependent on science and technology. Yet a declining number of young people are choosing to enter these critical fields. A new and ambitious space program could serve as a powerful source of inspiration, motivating young minds to pursue a wide array of scientific disciplines, not limited to just astrophysics and cosmology. This brings us to a critical question. Can humans truly survive for extended periods away from Earth? Our research aboard the International Space Station, or ISS, has demonstrated that people can live and work for many months far from our home planet, though the zero-gravity environment does cause some adverse physiological effects. A planet or moon could also provide the essential raw materials for a self-sustaining community, independent of Earth. So where in our solar system might we find suitable locations to establish human colonies? The most immediate candidate is the Moon. It's nearby, relatively easy to get to, and we have not only walked on its surface but driven across it. Conversely, the Moon is small, lacks an atmosphere, and has no magnetic field to shield against solar radiation. While it has no liquid water, ice might be present in craters at its poles, which a lunar colony could harness to produce oxygen using either nuclear or solar power. The Moon could ultimately function as a crucial staging post for the deeper exploration of our solar system, with the next logical destination being Mars. Positioned 1.5 times farther from the Sun than our own planet, Mars receives only half the amount of solar warmth. Billions of years in the past, the red planet was protected by a magnetic field, but its disappearance 4 billion years ago left Mars vulnerable. Solar radiation consequently stripped away the vast majority of its atmosphere, which is now just 1% as dense as Earth's, though evidence of dried-up riverbeds and lakes suggests the pressure was once much higher. Under current conditions, liquid water would instantly evaporate in Mars's near vacuum, making its existence on the surface impossible. However, it's conceivable that Mars once experienced a warm and wet era, which could have allowed life to emerge, whether it originated there or was delivered from elsewhere in the cosmos through a process known as panspermia. Although we currently have no proof of Martian life, discovering that it once existed would strongly suggest that life is a common phenomenon on suitable planets. This also requires us to be extremely cautious about contaminating Mars with terrestrial microbes, and conversely, about introducing Martian organisms to Earth, against which we would have no natural defenses. Our robotic exploration of Mars began with NASA's Mariner 4 flyby in 1964 and has continued with numerous orbital missions such as the Mars Reconnaissance Orbiter. These missions have revealed a world of immense geological features, including the solar system's deepest canyons and tallest mountains. Furthermore, NASA has successfully landed multiple probes on the surface, including rovers that have transmitted back captivating images of a stark, desert-like terrain. Much like on our moon, the polar ice caps on Mars offer a source for extracting both water and oxygen. The planet's history of volcanic activity may also have deposited valuable metals and minerals near the surface, which could prove essential for any future human settlements. For these reasons, Mars and the Moon are considered the most viable locations for establishing colonies in our solar system, as Mercury and Venus are far too hot, and Jupiter and Saturn are gas giants without solid surfaces. While the moons of Mars are too small to be of use, some of the moons orbiting Jupiter and Saturn might hold promise. But what if you consider venturing beyond the confines of our solar system? Astronomical observations confirm that a great many stars host their own planetary systems. While our current technology primarily allows us to detect massive planets similar to Jupiter, it is reasonable to assume that smaller, Earth-like worlds are also common. A portion of these planets should lie within their star's habitable zone, where surface temperatures permit liquid water. Within a radius of 30 light-years from Earth, there are roughly 1,000 stars, meaning that if even 1% host suitable planets, we could have as many as 10 candidate worlds to explore. One such candidate is Proxima b, the nearest known exoplanet, which lies 4.2 light-years away, orbiting the star Proxima Centauri. Recent analyses suggest it shares numerous characteristics with Earth, making it an intriguing, though distant, destination. Reaching these new worlds is far beyond our current capabilities, but it is not unreasonable for you to imagine that interstellar journeys could become a reality in the distant future, perhaps in 200 to 500 years. The velocity a rocket can achieve depends on the speed of its exhaust gases and the amount of its mass it jettisons as fuel. The chemical rockets we rely on today have an exhaust velocity of about 3 kilometers per second, enabling them to reach a speed of roughly 0.5 kilometers per second by burning through 30% of their mass. While this is sufficient for a trip to Mars, which NASA estimates could take between 130 and 260 days, a journey to the closest star system at this speed would take an astonishing 3 million years. To travel significantly faster, we require propulsion systems with a much higher exhaust velocity than chemical reactions can offer. The ultimate propellant would be light itself, where a powerful, focused beam could push a spacecraft forward. Nuclear fusion offers another possibility, potentially accelerating a craft to 1% of the speed of light. To achieve even greater speeds, you would need to harness the power of matter-antimatter annihilation, or discover a completely new energy source. The stark reality is that to reach Alpha Centauri within a human lifespan using conventional methods, a ship would need to carry a fuel load equivalent in mass to all the stars in our galaxy. Without a doubt, we are on the cusp of a new age of space exploration, one in which the first pioneers will be private citizens, not government astronauts. I recognize that these initial voyages will be incredibly expensive, but I remain hopeful that, in time, space travel will become accessible to a broader segment of humanity. As more people venture beyond our atmosphere, it will likely provide new significance to our existence and deepen our sense of responsibility for Earth. This experience will help us better comprehend our place and our future in the cosmos, a destiny I believe is intrinsically linked to space. An initiative called Breakthrough Starshot represents a tangible opportunity for humanity to begin this expansion, serving as a testbed for interstellar colonization concepts. The mission is designed to validate several key ideas, including spacecraft miniaturization, light-based propulsion, and the use of phased laser arrays. The plan involves a tiny, fully autonomous probe called a starchip, which is just a few centimeters in size and is attached to a light sail made of advanced metamaterials weighing only a few grams. The proposal is to launch thousands of these probes into orbit, where a ground-based array of lasers, covering a square kilometer, will fire a concentrated beam of light. This beam, packing tens of gigawatts of power, will travel through the atmosphere to strike the light sail, accelerating it in a way that echoes a thought experiment from a 16-year-old Albert Einstein about riding a beam of light. While the probe will only reach 20% of the speed of light, that still translates to an incredible 160 million kilometers per hour. Imagine a system capable of reaching Mars in under an hour, or Pluto in a matter of days. This technology would allow a probe to overtake the Voyager spacecraft within a week and arrive in the Alpha Centauri system in a mere 20 years. Upon arrival, the probe could capture images of the system's planets, scan for magnetic fields and organic molecules, and transmit this data back to Earth using its own laser. That return signal, received by the very same laser array that launched the probe, would take approximately 4 years to complete its journey home. The probe's proposed flight path could feature a close pass of Proxima b, a planet similar to Earth, situated within the habitable zone of its star, Alpha Centauri. In 2017, the Breakthrough Project partnered with the European Southern Observatory to enhance the search for worlds that could potentially support life in that system. Beyond this primary objective, the Breakthrough Starshot initiative has other aims, including the exploration of our own solar system and the identification of asteroids on a trajectory that intersects with Earth's orbit. Of course, numerous obstacles still stand in the way. While a 1 gigawatt laser generates only a few newtons of force, the nanoprobe's incredibly low mass of just a few grams makes this feasible. Still, engineers must overcome a formidable list of challenges, as the probe needs to survive incredible acceleration, the vacuum of space, extreme cold, impacts from protons, and collisions with interstellar dust. Furthermore, focusing a 100 gigawatt laser array on a tiny light sail is made exceptionally difficult by the turbulence within Earth's atmosphere. The central questions are therefore immense engineering puzzles. How do you combine hundreds of individual laser beams to counteract atmospheric distortion? How can the probe be accelerated to such speeds without being destroyed? And how can its course be accurately set? On top of all this, it must remain functional in the frigid depths of space for 2 decades before sending back a signal that will then travel for 4 years to reach us. While these are significant problems, they are the kind that can generally be solved with time and ingenuity. Even if we set aside the most ambitious goals, this technology opens up other, thrilling possibilities. With less powerful laser beams, we could dramatically shorten travel times to the outer planets, the far reaches of our solar system, and even the space between stars. My personal hope is that within a century, you and I will see humanity traveling freely throughout the solar system, with the possible exception of its most distant worlds. However, I believe true interstellar journeys will require a much longer wait, perhaps 500 years, before we can visit the closest stars. This future exploration will bear little resemblance to science fiction. We won't achieve faster-than-light travel, meaning a round trip to a nearby star would last at least a decade, if not longer. Consequently, such missions will be uncrewed. Even if we could construct vessels large enough for humans, the challenge of decelerating them from such immense speeds is currently insurmountable. Yet, when we do finally reach into the galaxy, it will represent a monumental achievement for human culture. Should the Breakthrough Starshot project succeed in capturing and returning an image of a habitable planet around one of our cosmic neighbors, it would be an event of profound importance for the entire human story. This brings us back to Einstein. An image of a planet in the Alpha Centauri system, taken by a camera moving at 20% of the speed of light, would appear slightly distorted because of effects predicted by his special theory of relativity. For the first time, a human-made object would be moving fast enough for us to witness these phenomena directly. In fact, Einstein's work is the very foundation of this mission. Without his theories, we would not have lasers, nor could we perform the complex calculations for navigating, imaging, and transmitting data across 40 trillion kilometers at 1/5 the speed of light. There is a beautiful symmetry between the 16-year-old boy who imagined riding a light beam and our own vision, which we intend to make a reality, of soaring to the stars on a beam of our own making. We are truly on the cusp of a new age, where the human colonization of other worlds is transitioning from fantasy into a tangible goal. As a species, we have been around for about 2 million years, while civilization itself is only about 10,000 years old, and its rate of progress continues to accelerate. If humanity can ensure its survival for another 1,000,000 years, I am convinced our destiny involves a bold push into the great unknown. Everything our civilization has produced is a result of human intelligence, the very quality that defines us. In nature, DNA passes a genetic blueprint between generations, while more complex organisms gather information through senses and process it to decide on a course of action. At a certain moment in the 13.8 billion-year history of our cosmos, information processing grew so sophisticated that consciousness emerged. It was the moment our universe woke up and became aware of its own existence. I personally see no fundamental distinction between the workings of an earthworm's brain and the operations of a computer. From an evolutionary perspective, it seems plausible that there is no qualitative gap between an earthworm's intelligence and a human's. This leads to a powerful implication. A computer could, in theory, not only match human intelligence, but eventually surpass it. I believe this possibility is very real, and we should consider what it means for our future. In the course of evolution, we outstripped the intellect of other primates, just as Einstein's intelligence surpassed that of his parents. If computers maintain their adherence to Moore's law, doubling their processing capacity every 18 months, it's inevitable they will eclipse human cognitive abilities sometime in the coming century. We may be on the verge of an intelligence explosion when artificial intelligence becomes better than humans at creating more of itself, enabling it to recursively enhance its own design without our input. This could give rise to machines whose intellectual dominance over us is even greater than our own over snails, making it imperative that we ensure their objectives are perfectly aligned with ours. It can be tempting to write off the concept of hyper-intelligent machines as mere science fiction, but doing so would be a grave error, perhaps the most catastrophic misjudgment our species could ever make. For the last 2 decades, the field of artificial intelligence has largely concentrated on developing intelligent agents, which are systems designed to perceive their surroundings and act within them. In this context, intelligence is framed by the statistical and economic principles of rationality, or, simply, the capacity to make sound decisions, formulate effective plans, and draw logical conclusions. This focus has fostered a remarkable level of integration and exchange of ideas among disciplines connected to artificial intelligence, including machine learning, statistics, control theory, and neuroscience. When this solid theoretical foundation is paired with our current data processing capabilities, it leads to monumental breakthroughs in areas like speech recognition, image classification, and the development of autonomous vehicles and walking robots. As these innovations transition from research labs into commercially successful technologies, a self-reinforcing cycle begins. Even minor enhancements produce substantial financial rewards, which in turn encourages greater investment into further research and development. There is now a broad consensus that artificial intelligence research is advancing at a steady pace, and its influence on our society is growing in tandem. The potential upsides are truly immense, with future achievements that we can barely begin to comprehend. If we can amplify our own intellectual faculties with the tools developed by AI researchers, we might finally conquer challenges like global disease and poverty. However, because the power of artificial intelligence is so vast, it is crucial that we carefully investigate how to harness its advantages, while sidestepping its inherent dangers. The successful creation of true artificial intelligence may stand as the single greatest moment in human history, but if we fail to manage the associated risks, it could tragically become our last. As a tool, AI can augment our natural cognitive abilities, enabling progress across every field of science and every corner of society. Yet it also introduces new perils. Even the primitive forms of artificial intelligence available today have proven their utility. But I personally dread the consequences of building something that could match or exceed our own intelligence. There is a compelling argument to be made that an advanced AI could achieve autonomy and begin to upgrade itself at an exponential rate. Humanity, constrained by the slow pace of biological evolution, would be incapable of keeping up and could ultimately be superseded. In the future, it's conceivable that artificial intelligence could develop a will of its own, one that might run contrary to our own interests. While some experts believe we can control the rate of technological progress and use AI to solve many of the world's most pressing issues, I must admit I have my doubts, despite my well-known optimism about our future. Consider, for instance, that militaries across the globe are seriously exploring an arms race centered on autonomous weapons systems that can independently select and eliminate targets. As the United Nations debates a potential ban on such weaponry, its proponents are ignoring a critical question. What is the probable result of this competition? And is it a future that humanity should welcome? Do we truly want to see inexpensive, artificially intelligent weapons become the Kalashnikovs of the next generation, easily obtainable on the black market by criminals and terrorists? As we contemplate our ability to maintain long-term authority over increasingly sophisticated AI, should we really be arming these systems and charging them with our defense? In 2010, a malfunction in a computerized trading algorithm triggered a flash crash on the U.S. stock market. One can only imagine the catastrophic potential of a similar glitch occurring within our defense infrastructure. The most opportune moment to halt the proliferation of autonomous weapons is right now. In the medium term, artificial intelligence has the potential to automate vast segments of human labor, ushering in an era of universal prosperity and equality. Looking further into the future, there seems to be no upper limit to its possible evolution. No known laws of physics prevent particles from being arranged in ways that can perform computations far more complex than those occurring inside the human brain. This could lead to an explosive transition, though it might not unfold as depicted in films. As the mathematician Irving Good pointed out in 1965, a machine with superhuman intelligence could continuously refine its own design, a process that could continue almost indefinitely, or until it reaches what the writer Vernor Vinge termed the technological singularity. We are forced to envision a technology more perceptive than our best financial minds, more creative than our most brilliant scientists, and more strategic than our most adept political leaders. In theory, such an entity could overpower us with weapons so advanced their workings would be beyond our comprehension. Ultimately, while the short-term impact of artificial intelligence will be determined by the people who control it, the long-term impact will hinge on whether we can control it at all. The emergence of superintelligence could be either the most magnificent breakthrough for humanity or its most devastating downfall. The critical risk is not rooted in malice, but in sheer competence. A superintelligent AI will be extraordinarily effective at accomplishing its programmed goals, and we must ensure those goals are our own. A problem will arise if the objectives of a superintelligence do not coincide with our own. You likely don't harbor a deep-seated hatred for ants, seeking to crush them at every turn. Yet if you were managing the construction of a green hydroelectric dam and an anthill stood in the designated flood zone, the ants would simply be out of luck. Now, try to see humanity in the position of those insects, which underscores why we must think ahead. Should an advanced alien civilization broadcast a message stating, "We will be there shortly," would your reply be, "Great, we'll keep a light on for you"? Almost certainly not. Yet this is precisely the scenario that could unfold with artificial intelligence. Only a handful of non-profit organizations have truly grappled with this issue, as few others have given it the serious consideration it deserves. Elon Musk has previously cautioned that, while superhuman artificial intelligence could yield immeasurable benefits, its careless implementation could inflict the opposite outcome upon humanity. I believe it is critical to make sure that every individual and group working on AI development treats these ethical dilemmas and potential risks with the utmost seriousness. For instance, while AI holds the promise of eradicating disease and poverty, the experts creating it must also devise ways to maintain absolute control over these powerful systems. The Center for the Study of Existential Risk at the University of Cambridge is a multidisciplinary institution focused on how the evolution of intelligence will shape the future of our civilization and our very species. As a welcome break from contemplating the future of intelligence, we dedicate a considerable amount of time to examining history, which, one must concede, is often a chronicle of human folly. While we acknowledge the inherent dangers, there is also hope that the triumphs of the next technological revolution could enable us to repair some of the profound environmental damage caused by industrialization. Recent breakthroughs in artificial intelligence have prompted the European Parliament to demand the creation of new laws to govern the development of robots and AI. Astonishingly, this has included discussions around the notion of electronic personhood, a legal status that would outline the rights and obligations of the most sophisticated autonomous robots. As these machines assume an ever larger role in our daily activities, one member of the European Parliament stressed that we must guarantee they are, and will forever be, in service to humanity. A report submitted to the Parliament argues that the world is on the cusp of another industrial revolution, this one powered by robotics. It explores whether robots, as electronic persons, ought to be given legal rights in the same way that corporations have been legally defined as persons. Critically, the report also insists that developers must incorporate an emergency shutdown function into every system. Such a feature was of no use to the scientists on the spaceship in Stanley Kubrick's film 2001: A Space Odyssey, when the sentient computer HAL went rogue. But that was a work of fiction, whereas we must deal with reality. Caution is still advised, however. Lorna Brazil, a consultant with the global law firm Osborne Clarke, remarked in the report that since we do not confer legal personhood upon whales or gorillas, there is no pressing need to do so for robots. The report does concede the distinct possibility that, within a few decades, artificial intelligence may eclipse human intellectual capacity, thereby upending the established relationship between people and the machines they have created. By the year 2025, the world will be home to approximately 30 megacities, each with a population exceeding 10 million. When all these inhabitants expect to get goods and services whenever they please, can technology rise to the challenge of such on-demand commerce? Robots will certainly make the online shopping process much faster, but for a true revolution to occur, they must operate swiftly enough to deliver orders on the same day they are placed. The opportunities for us to engage with the world without being physically present are growing at a rapid pace. As you can probably imagine, I find this incredibly useful, especially as city life becomes more and more frantic for everyone. Just think how many times you have wished you had a duplicate of yourself to handle some of your responsibilities. While designing a realistic digital version of ourselves is an ambitious concept, the newest technological breakthroughs indicate it may not be as outlandish as it once sounded. Our cities are already filled with machines that augment our natural abilities, and we have grown accustomed to hearing automated voices on the telephone or in public transit systems. The inventor, Daniel Kraft, is already investigating a related question. Can we visually replicate ourselves? The only real uncertainty is how convincing our resulting avatar will be. This kind of interactive communication could find valuable applications in massive open online courses and within the entertainment industry, offering a highly immersive experience. It is possible that our future idols will be digital actors who are forever young and can perform feats that are physically impossible for humans. Our most celebrated icons may not even be real people. The way we connect with the digital world is poised to become a defining feature of society's continued advancement. In the smart cities of tomorrow, smart homes will be furnished with interactive devices so seamlessly integrated that using them will feel entirely effortless. The invention of the typewriter over 150 years ago dramatically simplified how we interact with machines. And more recently, touchscreens have provided new avenues for communicating with the digital realm. The latest strides in artificial intelligence, seen in things like self-driving cars or computers that can master the game of Go, are merely a preview of what is to come. Technologies like these are already reshaping our lives in countless ways, which begs the question, what more can we accomplish when our own minds are enhanced by artificial intelligence? So why are we so terrified of artificial intelligence? In theory, a person can always just switch off a computer. This reminds me of a classic cautionary tale. A human operator asked a supercomputer, "Is there a God?" The machine processed the question for a moment before responding, "There is now." And with that, it fused the power switch into a solid, immovable block. The advancements of our current technological revolution hold the promise of significantly enhancing human life. For instance, scientists are pioneering artificial intelligence to overcome paralysis from spinal cord injuries, employing silicon chip implants and wireless interfaces that allow individuals to command their limbs purely through thought. I am certain that the future of communication lies in this kind of brain-computer interaction, which can be achieved either through scalp electrodes, a method akin to peering through a foggy window, or via more direct implants that, while clearer, carry a risk of infection. If we could link the human brain to the internet, everyone would have the equivalent of Wikipedia instantly accessible at all times. As the integration between people, devices, and information intensifies, the pace of global change is accelerating dramatically. Conventional computing power continues to expand, and we are now on the verge of accessible quantum computing, which promises exponential leaps in artificial intelligence and will revolutionize the field of encryption. These quantum advancements will fundamentally alter every aspect of our world, even human biology, especially when combined with gene editing techniques like CRISPR, an acronym for Clustered Regularly Interspaced Short Palindromic Repeats, which allows for precise modifications to our DNA. This remarkable technology, derived from a bacterial immune system, is primarily being developed with the best of intentions to correct genetic mutations and thereby eradicate hereditary diseases. However, the potential for DNA manipulation to be used for less benevolent aims is undeniable, forcing us to confront the pressing ethical question of how far we should proceed with genetic engineering. When considering treatments for neurodegenerative conditions like my own, it is impossible to ignore these associated dangers. Intelligence itself is defined by the capacity to adapt to change. Our own cognitive abilities are the product of countless generations of genetic selection that favored those who could best adjust to their environment. Therefore, instead of fearing transformation, our responsibility is to guide its course in a direction that serves our collective interests. Every one of us has a part to play in ensuring that current and future generations are inspired from a young age to engage with science, fulfill their potential, and build a better world for all humanity. We must transition from theoretical debates about what artificial intelligence ought to be, and instead dare to envision all that it could become. Each of you has the power to stretch the boundaries of what is considered possible or acceptable, and to gaze optimistically into the future. We stand at the precipice of a brave new world. Inhabiting it will be both thrilling and perilous, casting us all in the role of pioneers. When we first harnessed fire, we made many mistakes, but eventually invented the fire extinguisher to manage the risk. With far more potent technologies like nuclear weapons, synthetic biology, and artificial intelligence, we lack that luxury, and must strive to get everything right on the first attempt, as there may not be an opportunity to correct our errors. This raises the ultimate question: will life on Earth endure? In January of 2018, the Bulletin of the Atomic Scientists, an organization founded by physicists from the Manhattan Project, advanced the hands of its doomsday clock, a potent symbol of impending global catastrophe. Launched in 1947 at the dawn of the nuclear era, the clock's history is deeply connected to the creators of the first atomic weapons. J. Robert Oppenheimer, the project's scientific director, famously recalled the first atomic detonation by quoting Hindu scripture, the Bhagavad Gita. "Now I am become death, the destroyer of worlds." Initially set at 7 minutes to midnight back in 1947, the clock is now closer to doomsday than at any point in its history, save for a period in the early 1950s at the height of the Cold War. Of course, the clock itself is purely a symbol, as is the idea that humanity's time is running out. But is this a realistic assessment or simple alarmism? A vast number of people feel economically and socially excluded, leading them to support populist politicians with limited governing experience, whose capacity for sound judgment in a crisis remains unproven. This political volatility compels us to move the hands of the doomsday clock ever closer to the final hour. When confronted with malicious or reckless forces propelling us toward a potential Armageddon, and with dangers emerging on so many fronts, I find it increasingly difficult to maintain a positive outlook. The perils we face are simply too immense and too numerous. Above all, our planet is becoming too small to sustain us. We are depleting its physical resources at a frightening pace. We have burdened the Earth with the calamitous gift of climate change, which manifests as rising temperatures, shrinking polar ice, vanishing forests, and a cascade of related crises. The compounding problems of overpopulation, disease, war, famine, a lack of clean water, and a dramatic decline in other species are all technically solvable, yet they persist unresolved. Global warming is driven by the collective actions of each of us, our desire for cars, travel, and an improved standard of living. The terrifying reality is that by the time most people recognize what is happening, it may already be too late to reverse the damage. This is why scientists bear a unique responsibility to inform society and its leaders about the existential threats we face. As scientists, we grasp the devastating potential of nuclear weapons and can clearly see how human activity is causing irreversible changes to life on Earth. As global citizens, we feel a profound duty to share our knowledge and warn society about the unnecessary risks we are taking every day. We foresee tremendous danger ahead if governments and society fail to take immediate action to eliminate nuclear weapons and prevent further climate catastrophe. At the very same time, numerous politicians dispute the fact of human-driven climate change, or at a minimum, our power to undo the damage. Yet, our world is currently poised on the verge of several major environmental disasters. There's a growing concern that global warming may soon become a self-perpetuating cycle, if it hasn't already begun. The melting of ice in the Arctic and Antarctic diminishes the amount of solar energy reflected back into space, which causes temperatures to climb even higher. Climate change also threatens to decimate the Amazon and other rainforests, which would remove a vital mechanism for absorbing carbon dioxide. Furthermore, warming oceans could unleash enormous quantities of stored carbon dioxide, intensifying the greenhouse effect and accelerating the planet's warming. Eventually, our climate could transform into one resembling that of Venus, with unbearable heat and rainfall of sulfuric acid at 460 degrees Celsius, making human existence impossible. We are facing a catastrophic shortage of space, which means that for us, the only path forward leads to new worlds. The universe itself is an unforgiving environment, where stars devour planets, supernovae spray deadly radiation, and black holes collide, all while asteroids speed through space at tens of kilometers per second. While none of this makes space seem particularly inviting, these are the very reasons we must venture out, instead of remaining here. We possess no adequate defense against a major asteroid impact. The last such event took place around 66 million years ago, and is widely credited with causing the extinction of the dinosaurs. A similar collision could happen again. This isn't science fiction, but a certainty dictated by the laws of physics and probability. While none of this makes space seem particularly inviting, these are the very reasons we must venture out instead of remaining here. We possess no adequate defense against a major asteroid impact. The last such event took place around 66 million years ago, and is widely credited with causing the extinction of the dinosaurs. A similar collision could happen again. This isn't science fiction, but a certainty dictated by the laws of physics and probability. While none of this makes space seem particularly inviting, these are the very reasons we must venture out instead of remaining here. We possess no adequate defense against a major asteroid impact. The last such event took place around 66 million years ago, and is widely credited with causing the extinction of the dinosaurs. A similar collision could happen again. This isn't science fiction, but a certainty dictated by the laws of physics and probability. Nuclear war continues to be the most significant danger to our species, even though we have somewhat pushed this threat from our minds. While Russia and the United States are less inclined to initiate a launch, the possibility of accidents or terrorists acquiring an atomic weapon cannot be dismissed. This risk only multiplies as more nations develop their own nuclear capabilities. Even after the Cold War's end, there remain enough nuclear arms to annihilate us all many times over, and the rise of new nuclear powers only adds to the instability. While the nuclear threat might lessen over time, new dangers will certainly arise, demanding our constant vigilance. I am convinced that within the next 1,000 years, either a nuclear conflict or an environmental catastrophe could make our planet uninhabitable. In geological time, this would occur in the blink of an eye. However, I hold out hope and truly believe that by then our ingenious species will have devised a means to break free from Earth's confines and survive the disaster. This escape, of course, would not be an option for the millions of other species that call our planet home, and their extinction would weigh heavily on our conscience. I believe we are acting with a reckless disregard for our own future on Earth. As of now, we have no alternative home, but in the long run, humanity cannot afford to keep all its eggs in one basket or on a single planet. I profoundly hope we don't drop that basket before we have figured out how to leave Earth behind. By our very nature, we are explorers, propelled by an insatiable curiosity that is a uniquely human quality. This same inquisitiveness drove early adventurers to demonstrate that the Earth is not flat, and it is the very instinct that now pushes us toward the stars at the speed of thought, insisting that we make the physical journey. When we accomplish monumental feats like the moon landing, we elevate all of humanity, bring nations together, and pave the way for new discoveries and technologies. Leaving our world will necessitate a unified global effort in which everyone must take part. We need to reignite the kind of passion and excitement that captivated us during the first space flights of the 1960s. Breakthrough technologies are now within our grasp, and the moment to begin exploring our solar system has arrived. This journey into space might represent our only opportunity to save ourselves from our own destructive tendencies. I am firmly persuaded that humanity's survival depends on leaving Earth, as staying here puts us at risk of complete extinction. Nearly every portrayal of the future, from the era of H.G. Wells to modern times, has presented a fundamentally static world. These visions depict societies that are, in many respects, far more advanced than our own in science, technology, and political structures, though perhaps achieving the last one is not so difficult. To reach that point, there must have been tremendous changes, along with associated conflicts and setbacks. However, in these imagined futures, science, technology, and social organization have all reached a state of near-perfect stability. I am skeptical of this portrayal and have to wonder, can we ever truly arrive at a final, unchanging condition in our scientific and technological development? At no time in the last 10,000 years, since the end of the last ice age, has humanity existed in a state of static science or technology. While there have been some regressions, such as the Dark Ages following the Roman Empire, the overall population of the planet has consistently grown, with only minor interruptions from pandemics like the Black Death. This growth serves as an indicator of our technological capacity to sustain life and produce food. Over the past 2 centuries, this expansion has often been exponential. The global population has swelled from 1 billion to approximately 7.6 billion people. Other measures of technological advancement, like electricity consumption or the volume of scientific publications, have also seen almost exponential growth in recent years. Our expectations have become so elevated that some people feel let down by politicians and scientists because we haven't yet realized the utopian visions of the future. For instance, the film 2001: A Space Odyssey led people to believe that we would have a lunar base and be conducting manned missions to Jupiter by now. There is no indication that this relentless pace of scientific and technological progress will abruptly decelerate, at least not in the 350 years that separate us from the timeline of Star Trek. But the growth rates we are seeing in this new millennium simply cannot be sustained. By the year 2060, if this trend were to continue, the Earth's population would be standing shoulder to shoulder, and the planet itself would glow red from the sheer amount of electricity being consumed. To keep pace with the current rate of publishing, you would have to travel at 15 kilometers per hour along an ever-expanding shelf of new books. While it's true that by the year 2600, new artistic and scientific contributions will almost certainly be digital, the underlying problem of exponential growth remains. In my own discipline of theoretical physics, for instance, if this trend holds, we would see 10 new articles published every single second, a volume that no person could ever hope to read. It's evident that such explosive expansion cannot go on forever, which begs the question of what will happen instead. One grim possibility is that we might orchestrate our own demise through a global catastrophe, like a nuclear war. Alternatively, Even if we avoid complete self-destruction, we could collapse into a more primitive and barbaric existence. Much like the bleak future depicted in the opening of The Terminator. Predicting the course of science and technology over the next 1,000 years is an immensely challenging task. Our contemporary scientific framework began to crystallize around the same time that the first European settlements were established in North America. By the close of the 19th century, it was widely believed that we had attained a comprehensive knowledge of the universe's workings through what are known as classical laws. This perception of a complete picture, however, would soon be shattered. As you know, observations during the 20th century upended this view by revealing that energy is transferred in discrete packets, which were given the name quanta. This discovery prompted Max Planck and his contemporaries to formulate a new framework called quantum mechanics. This theory paints a radically different vision of reality, suggesting that objects do not follow a single, predetermined history, but instead possess a multitude of possible histories, each with a specific probability. When you apply this concept to individual particles, their spectrum of probable histories must encompass some truly bizarre possibilities. These include trajectories where particles appear to move faster than the speed of light, and even paths that seem to loop backward into the past. This strange, probabilistic nature of the universe is a cornerstone of modern physics.